Okay, here we are, R6b. You know, we get done with this lesson, and we have, I think, one more, and then we'll be done with the review, and we can get on with the new stuff, and maybe you're okay with the review, I don't know. So we've got example 3. That 3 is not the index. The index there is 2. That 3 is just a number being multiplied by the square root of 8x squared. So when you're writing these, make sure you write things so that people don't get confused at what you're doing there. So it says perform the operations indicated. So what we're going to do is we're going to simplify each one of the terms, this one and this one, before we actually do the subtraction here. So what we're going to do is we're going to look at this 2 and we're going to write it at, or this 8 and write it as 2 cubed x squared, and then minus 5, and this can't be simplified at all, so we'll just write it that way. Okay, so again, what do? Index 2 goes into 3, this exponent, one time, so that means we pull 1, 2 out, and we're left with 1 left over. Okay, 2 goes into 3 once with 1 left over. 2 goes into 2 one time with none left over, so the x completely disappears. So what we end up with for this right here, simplified, is 6x square root of 2. Okay, notice here, I have a radical sign there that I want to see if I can reduce. How do I know if I can reduce it? If one of my exponents is bigger than my index, or the same as. My index is 2. So, when you have a number or a letter with an exponent or without an exponent, it's actually a 1, and that's smaller than my index, so nothing happens with that 2, it just stays there. But this 2 goes into that 2 one time, so 1x comes out with none left over. Now notice what I have here, 6x square root of 2 minus 5x square root of 2. The only time I can combine two terms like that is if the index is the same, whether it's a square root or a cubed root or a fourth root, and everything inside the radical sign is the same. If that's the case, you can combine these two terms like we can now. And you combine these as if the square root of 2 was a variable. So it just kind of tags along. So you have 6x minus 5x, which is 1x, and the square root of 2. So you don't have to write the 1. Okay? So the square root of 2, it doesn't do anything. It's just like when you say 3x minus 2x is 1x. You don't do anything with the x's, you just subtract the numbers in front of the x's. The same is true with a radical. Just kind of pretend like it's a variable, and you'll do fine with it. Alright, let's look at part B, and then I think we're about done with this lesson, and you can kind of get on with your life. See if I can erase some of this stuff. Alright, so let's put B up here. 4 square root of 3 plus square root of 2 times square root of 3 minus 5 square root of 2. Alright, when you have something like that, you've got two binomials, and each one of the binomials obviously has two terms in it. When you've done things like this, like x plus 2 times x minus 3, what do you do to solve that, or to simplify that? You do the FOIL method. We're going to do the same thing with this. Okay, we just have radicals there. So, FOIL, F-O-I-L. So we're going to do the first, this times this. So we get 4 square root of 3 times the square root of 3, which gives me 4 square root of 3 squared. Okay, because it's this times this is the square root of 3 squared. Now, you can do a lot further than this in your head, but I'm just doing it step by step just for the time being. The O, the outside, so it's 4 square root of 3 times negative 5 square root of 2. And that gives me a negative 20, 5 times 4, and square root of 3 times square root of 2 is square root of 6. And then we do the inside. Square root of 2 times square root of 3 is square root of 6. You can multiply anything. Okay, and then last, square root of 2 times negative 5 square root of 2. So that gives me a negative 5 square root of 2 squared. Okay, square root of 3 with an exponent of 2. Anytime the radical index and the exponent are the same, you can just take the sign and the exponent off. Okay, let's add those. We can add those, whoops, because now I can't erase, but alright, so we're going to take negative 20 plus 1 square root of 6. That gives me negative 19 square root of 6 minus 5 times, remember, index and exponent are the same, you can take the signs off. Alright, so that gives me 12 minus 19 square root of 6 minus 10. 12 minus 10 is 2. And that's as far as you can go in this particular problem. Can't simplify it any more than that. Okay, so let's look real quick. Boy, I guess we do have a little bit further to go here. Holy cow, this is a long chapter. We're going to look at Pythagorean theorem for just a minute. And Pythagorean theorem, boy, you've had that since about kindergarten. And remember, Pythagorean says a squared plus b squared equals c squared when you have a triangle, a right triangle. And a and b, it can be any of the sides, and the longest sine is c. So it's just saying if we square one side and we square the other side and add them together, that distance is going to be the same as if we squared the c. So for instance, if I have what's called a 3, 4, 5 triangle, okay, what Pythagorean says is one side squared plus the other side squared equals the hypotenuse squared. So this is going to be 9 plus 16 equals 25, and that's a true statement. Okay, so given that bit of information, we can solve a lot of problems, except world peace. All right, so example 4 says a surveyor places poles at points A, B, and C. Okay, so let's just make, get rid of that. We've got our A, B, and C. All right, and what about the surveyor? What does it have? This is 25, according to the little drawing. This is 47. And what they're interested in finding out is how far it is from here to here. That's what we're looking for. We're looking for the hypotenuse using a squared plus b squared equals c squared. C is always, always, always the hypotenuse. Alright, so we take one side, doesn't matter which side, and at the other side, and that gives me c squared. Get your handy dandy calculator out, and you'll end up with 2209 plus 625 equals c squared. Now, if you remember, in order to get rid of the squared, if we take the square root of both sides, the square root sign goes away. And this just ends up being, or a squared sign goes away, and it ends up just being c. So 2209 plus 625 is 2834. And that equals c. So take your handy dandy calculator out there, take the square root of 2834, and you get a number similar to 53.2, or approximately. That's what that symbol means, is approximately 53.2 yards. Okay, let's go to top of page 43. Rationalizing denominators or numerators. The fun just continues, doesn't it, as far as these radicals are concerned. Some reason I really like radicals. I don't know, maybe because they've always come a little bit easy for me. Okay, those two mean the same thing. And what we notice here is we have a radical sign in the denominator. We cannot have a radical sign in the denominator. It's kind of like taking a fraction, 2 over 4, and leaving that as your answer. It's not reduced. It's not simplified. So what we do is rationalize it. We take it from an irrational number and make it into a rational number. We take it from a square root number and take away the square root sign. All right, so the way we do that is, in order to get rid of this radical sign right here, we multiply both top and bottom by a number that when we multiply it times this number, the exponent becomes the same as the index. So I'm looking for a number here to multiply by the square root of 2 so that this index and this exponent are the same, because what have I said? When the index and exponents are the same, all of this goes away and we just get 2. And we have rationalized it. The rational sign, the radical sign, has disappeared. Okay, so a lot of people teach it differently than that. I teach it this way because later on it will bite you in the butt if you don't learn it this way. Alright, so what do I multiply that in order to get as an answer? It's kind of going backwards, that for my denominator. Well, I multiply it by the square root of 2, right? Because the square root of 2 times the square root of 2 is the square root of 2, the quantity squared, right? And that's what I want. It is going to be, when this index is 2, you pretty much multiply top and bottom by whatever's on the bottom, under the radical sign. Okay? But we'll look at some other ones later. So square root of 3 times square root of 2 is the square root of 6. So we get as an answer square root of 6 over, and because that is written where the index and exponent are the same, I can take the radical sign off and get that for an answer. Alright, let's look at B. And this is where it can oftentimes bite students in the hiney because it doesn't work the way a lot of teachers teach it. Okay, so what am I trying to do here? I'm trying to get rid of the radical sign down here. So what I'm trying to do is I'm trying to find a number to multiply the cubed root of 9 by so that I can take the cubed root of something. So let's say I take the cubed root of 9 times the cubed root of 2. That gives me the cubed root of 18. Is there a cubed root of 18? No. So what if I took this times the cubed root of 3? Cubed root of 9 times the cubed root of 3 is the cubed root of 27. What is the cubed root of 27? Is there one? Yes, there is. It's 3. So you just kind of fish around to try to find out, all right, what can I multiply this by so that when I multiply these two, I can actually take the cubed root of it and get a number, an irrational, or get a rational number. I want to get rid of the radical. And that's what you choose to multiply there. Now, if you don't pick the right number, it's okay. I mean, what if I were to take this cubed root of 9 times, let's say, the cubed root of 81, or I'm sorry, the cubed root of 9. 9 times 9 is 81. Is there a cubed root of 81? No. So, you know, it makes it easier when you can find one that you can go, oh, if you know your cubed roots, okay, 9 times 3 is 27, cubed root of 27 is 3, good to go. So now I'm going to multiply my top by the same thing. And I'm done. Okay, because there is no cubed root of 21. So that's the key here. You're multiplying the top and bottom by something. Index is always going to be the same. Whatever this index is, this index needs to be. But the number in here, you want to multiply it by a number so that you can take the cubed root of the product of these two. Okay, so that's a key part here. All right, let's keep going here, and I'm going to stop at 13 or 14 minutes, and we'll go into the next video.